And while we are actually flying in the face of risk reduction here as we compete for eyeballs with the NFL draft, but nevertheless, I am Will Stoffers, an eccentric blend of data science and the arts. My computational aero career has been a decade of visual storytelling with data, and from flight test to Dancing with the Stars, I've been inside the pressure cooker. Since my work frequently draws from the arts, we'll stay in the kitchen and enter the world of a restaurant group. Gin and Luck has multiple revenue streams. Here, we see books and restaurants, with each revenue type affecting the other. More concretely, Gin and Luck wants people using their book, Cocktail Codex, and they also want people dining at their dinner restaurant, for example. When the book authors and restaurateurs are the same people, they want diners engaged on both fronts. But let's focus on Cocktail Codex first. The book's idea is similar to the French mother sauces in that all recipes derive from 6 recipe families. I analyzed each recipe family to help address 2 customer loyalty problems. Here are 2 scenarios that can be improved by the same machine learning application. First, consider Jack, who normally makes one complicated recipe out of Cocktail Codex. When he's out of something, how does he choose another recipe that feels familiar? Remember, if he looks for a similar recipe elsewhere, that's bad. Diane's situation is harder. She wants to dine with Gin and Luck, but she thinks about dealing with the wait, the higher prices, all to order something unfamiliar and then not like it. Obviously, if she goes elsewhere instead, that's bad. We'll call this sententia churn, losing a customer during the decision-making process. Diane's is a restaurant decision and Jack's is for a recipe. In both cases, we've snatched defeat from the jaws of victory. So I wrote a simple proof of concept to keep Jack and Diane with the Gin and Luck brand. It uses NLP, which stands for natural language processing. NLP can predict how strong a match the user input is for each recipe family from Codex. Since Jack and Diane both own Cocktail Codex and they know what they've liked before, they can input historical orders and see which families they like most. Encountering an unfamiliar drink, NLP will predict a family and they can compare it with their preference as a first step toward a personal recommendation. But what is this prediction actually based on? The NLP model trained on recipes from Codex, and the initial training set is not evenly distributed, but there are solutions for that. It also requires user input, and we have to clean that input up. If Jack puts in a recipe from the book, using page numbers is cheating, so that has to go. And the easiest pattern for the computer to learn involves word frequency. But I want it to group certain things, like measurements, and I actually train the algorithm on these words or groups called tokens. It's no surprise that the words bitters and twist are tied for the top old-fashioned token, being the defining ingredient and defining garnish for the family. Likewise, the defining martini ingredient is vermouth, unless you're Winston Churchill. The word cold makes sense for the highball family, since most of the drinks have bubbles, and the colder the liquid, the longer you keep your bubbles. For the dense flip family, more spirit makes sense to cut through the egg and cream, whose proteins soften the spirit's bite. The daiquiri and sidecar are trickier. They're both types of sours, which makes it harder for humans to distinguish between them. Sidecars tend to have more ingredients since they're sweetened with liqueurs instead of the daiquiri's syrup. And sidecars tend to favor lemon, while daiquiris favor lime. But now that the computer has patterns, what is considered success? I mean, they're just drinks, this should be easy, right? Unless several human experts disagree on some. Take the Tom Collins, for example, half daiquiri, half highball. Since I'm not training a debate model, I solve this with a top 2 accuracy metric. That means when the score is 0.8, 80% of the recipes Jack asks about will have the truth in the top predicted pair. Using this metric, the model scored 92% on unseen recipes, and Gin and Luck is happy with that. But less happy with these 2. The model took advantage of the top 2 scoring and technically got Jack's questions correct. But top 2, it's really intended for hybrid recipes like the Tom Collins or a pina colada. For those, we'd want probabilities near 50%, not in the single digits. It did get 2 of Jack's questions completely wrong. The truth was 3rd highest for one and 4th for the other. But in general, this proof of concept seems promising, and it would not have been possible without the support of Jin and Luck. So a really big thank you to them. And the floor is yours for questions.